So this is your week 4 for your problem solving session. So this time around, we would be discussing on the topic of Fourier transform. So I found even Fourier transform, this topic is also our strategy. So when assignments are out, so I hope you'll be going through that. The last topic which we're discussing, this linear algebra. So there were a few things I think I maybe missed out in case I tried to discuss every important stuff which were there in your assignments and also uh, uh, as far as your lecture goes. So I tried to mm, pick the important questions out of all of them and have presented right before the end. We have discussed them over last 3 weeks and but still, because this is really a time constraint thing, so we cannot do the whole thing. If there is something, if I am missing out important, you can let me know. We can discuss it anytime you wish. So we can discuss during this problem solving sessions, or also you can put your queries in the discussion forum. So okay, but for now, we'll discuss a Fourier series. So uh, this will be some important topics that we'll be focusing on this session. So uh, Fourier series. So I think how many weeks did Fourier series lectures have started? Like how like how many weeks ago it started? Could you just tell anyone? I hope it is just a week ago it started. Uh, but anyways, okay. So we start with Fourier series. So we'll see some useful problems right here that would also help you to solve assignments. So here the definition of Fourier series goes like this. So what is policies, why do we do this, basically you may remember last time around when we were discussing linear algebra. So then we talked about linear basis and orthonormality and linear combination of basis vectors and all those stuff. So uh, while the discussion was going on, we looked through various examples. One of the example that I tried to uh, talk about during our last session was a polynomial function. So let's say this is that function, and we try to prove that that polynomial function can also form a vector space. As if we are talking about some Pn, I mean Pn polynomial, where n represents the degree of that polynomial. So that actually we can use to map that to Rn plus one vector space. So here also, what the uh, sole aim of Fourier series is, we take a function and we expand in terms of its basis, or you can say um, these are like basis vectors. You can say uh, this basically the entire thing is uh, power series expansion. So for every any given function, you can take a power series expansion, which is actually which is often denoted as this. So in this power series expansion, you can think of this x's are like your basis and alpha n's are your coefficients. So and they that is basically, you can say, expansion of a function in terms of its basis vectors, or or uh, yeah. So that is for any arbitrary function that you can say, like if you are doing a power series expansion of that function f of x, then you end up with a sum of different terms. So each term will correspond to a basis vector. So that was the thing that which we have gone through your last lectures. You have seen those things often, very often, during your last topic discussion of Fourier series. Linear algebra. So in Fourier series, what we do, we take a function which is periodic, and we try to expand them uh, in terms of cosines and sines. So you will see that this is also a expansion of a function, or a expansion of a periodic function in terms of basis function, which comes in uh, like which comes in cosines and sine. So why I'm calling this as a they form a orthonormal basis. Why I'm calling this as they form a basis. You'll see that these relations will ensure that, because we know that when we used to write even in vector spaces. So suppose if we had a vector like this, then you can able to write them a1, e1, a2, e2, and so on. We used to write them. So e1, e2, these were your basis vectors. So we were basically expanding them in terms of uh, in their basis. So this we used to expand them in the in terms of their basis. So this is basically linear combination of various basis vectors. So that is also exactly happening in this series expansion, or this expression. This f of x you can write exactly in terms of linear combination of basis. That is this sine and cosines together they form a basis, including one. So one basically corresponds to cos 0x. So this n goes from 0 to infinity. So if you have cos 0x for n corresponding to 0, then that would correspond to 1. So you have 1 cosine nx and sine nx. So, and why I'm calling this basis, like how to ensure that, like here you saw last time when we had a v vector, we were expanding in terms of this basis vectors. We always said that these basis vectors are orthonormal. They form an orthonormal basis. That means this e1 and e2, when we used to take the inner product, then they used to give uh, 0, that is they are orthogonal, and also they are normalized. And that means for any arbitrary en, like we used to have this kind of relation. So that is the feature of basis vectors, or when we used to expand for any vector in a given vector space, the basis vectors must come in a way that they should satisfy these conditions, this orthonormality. So that is how you also have to answer whether this uh, uh, cos and sine functions in this uh, expansion of a periodic function f of x would also have the same feature. So that is here you can see when you like for this integral. So this integral is like the uh, inner product version of uh, for functions, or like for if you are taking inner products uh, for some vectors, but in terms of functions we define in terms of overlap integral, or this integral basically represents this inner product. So you see that if I take some arbitrary sign and then I take this overlap integral with cosine, you will see that you will always get 0. So as long as this, yeah, so this will always be true. Like you can just simply take any, for example, you take n equal to 1, and you take an n equal to 1, or sorry, I mean n equal to 1 or n equal to 2, like for any value of m and n, you will find that this will always be 0. So that means this sine and sine x or cos x or uh, sine x, sine 2x. Like you take any uh, combination, or like you will find that this integral will always um, will go to zero. So that ensures that this sine x cos x they form a they are orthogonal to each other. So if their overlap integral goes to zero, and the same you can check for this case also. Like what happens in this case, uh, if you have uh, m not equals to n, then your integral will always corresponds to zero. If you have n equal to n, then your integral always be uh, equal to some constant. That's fine. So that means like here, so whenever you take like integral of some sin x or some cos 2x, cos 2x, uh, so only then you can get non-zero value. Otherwise, for all other cases, like you will get zero. So that ensures your that actually gives your orthonormality condition. So like when you are taking the same thing, it's basically you are taking the overlap integral with itself, cos 3x, cos 3x. So that will again give me zero. But if I uh, make it cos 3x and some cos 4x or cos 3x or sin x, or any other like a combination that you think, that will always give you zero uh, in this interval minus pi to pi. So that means this cos any two such functions when you are taking like which is giving zero, they basically correspond to orthogonality condition. Otherwise, if they gives you non-zero, so non-zero you can see only appears when they are same. In both these functions, they exactly are same. So that is basically is actually you can see that they correspond to normalization condition. So that is how you see orthogonality in this choice of uh, basis functions, sine and cosines. So because they construct a basis, because of the orthogonality feature, they can form a basis, and you can expand your functions. So if you are calling your polynomial as a vector, or you can think of as a like last time as we said, like it can map to Rn plus one dimension vectors. Then uh, it should also be able to be expanded in terms of its basis. And these coefficients basically are represented or defined in this way. So how this is obtained, like this is again obtained using this orthogonality condition. If you put this orthogonality condition uh, back here in this uh, expression, you can get this an and bn's. So if you can see, if I uh, for example, if I in this expression, if I integrate this f of x on both sides, let's say I'm integrating this on both sides, and here and I'm integrating it, let's say with cos nx, like I multiply cos nx here, and also I multiply cos nx here, the entire thing, and when I integrate them, you will see that like the first term will give you n cos n square x. That will give you some an with and I'm integrating under this limit, that will give you some a. But this term, the second term right here, that will actually under the integration, that will give you uh, zero value. So this is coming from this thing. So on the second side, on the second term, I was having some sin nx and cos nx. So that will go become zero due to this condition. And the first condition, which I said, the cosine square x, that will be non-zero because of this thing which I was telling. they will give some pi will upon the integration. So like these all things like I think they are already better explained to you in your lectures by Aditya Sharma. So if you're still having some problem in knowing this details, like you can always ask, like we can discuss it. So before now, like you can just check the form or expressions, these uh, definitions, so which may come useful for solving problems. So this is what A and B and B and C. So yeah, we always do this Fourier series expansion for periodic functions or non-sinusoidal periodic functions. We are basically we convert non periodic, sorry, uh, non-sinusoidal uh, periodic functions to sinusoidal periodic functions. Or otherwise, like you expand your uh, uh, non-sinusoidal periodic function in terms of their orthonormal basis of sines and cosines. So, here is just a question to see like how you can expand if a function in terms of their uh, Fourier basis. So sometimes the people also call this sine and cosine basis is Fourier basis. So uh, in this question, let's see what is given. So here there is a function f of x is equal to x, and uh, here this f of x is defined for this minus pi to pi interval, or this x value actually goes from minus pi to pi, and at f of plus pi and f of minus pi, this is actually giving you 0. And then further, they, it is a periodic function. So that is the unnecessary part of it. Like we are doing Fourier series expansion for periodic function, or otherwise for non-sinusoidal periodic function. Periodic functions, but they are not necessarily have to be sinusoidal. So in this case, like if you want to picturize this function, so this can be like, so uh, let's say f of x is here, this is x-axis. So here f of x is x, so something that goes like this. Then this is pi, this is minus pi, and like this. This is the periodic function, so it will repeat again after like if I'm here. So it should be 2 pi minus 3 pi. So this will keep repeating. So because this is a periodic function, and similarly, I will have a repetitive behavior on this side too. This is 2 pi, and this will be 3 pi. So here in this case, like it is asking us to calculate Fourier coefficients in the representation in this form. So the thing is like here you have to expand this function in terms of this exponentials. So we'll come to this like what is this exponential later on. So like you have to calculate something where this n actually goes from like a minus infinity to infinity. So and goes from like minus infinity to plus infinity. So so um, so the now like you can see, but we are not doing here. Just you have to um, do this Fourier series expansion for only for this period minus pi to pi, because in other and rest throughout the space it is having the same periodic behavior. So you can just like expand it within this minus pi to pi limit. So the thing is like you have to expand this in terms of um, like something e is for minus ix, then I2x, I3x, and so on. And this, like here, I was taking this kn value to be something 1, 2, 3. So it can also have minus 1, 2, 3. So exactly it like it would not be 1, 2, 3, because here kn would be something 2 pi n l. So let's say I'm just normalizing this vector to be some integer like 1, 2, 3, and something. Let's just think this game can have 1, 2, 3, and all other integer values. So for this case, like if you would check, you will get. So here I forgot to write this terms. This will be f1. Or otherwise, let me write it again. So the thing is like you have to expand this function in terms of like in this way k1 f tilde, so on. You have to do this. Earlier what we were doing, so as I showed you the definition of Fourier series, so it was like in terms of cosines and sine. So that was the case. We were expanding the function in this fashion, and so on. We also had this sine terms. So yeah, but now you have to expand in terms of these exponentials. And again, this exponential will also have this orthonormality feature. That's why we are able to expand, because this is we are expanding in terms of some orthonormal basis. So here, if you would see, let's say here in this question we have to calculate Fourier coefficients. So Fourier coefficients in this case is this f tilde. So this f tilde n, which is this is what we need to calculate. Like we have to like if we are expanding this in terms of cosines and sine, then we would have required to calculate a's, this ans and bns, or a1, a2, and so on, and b1, b2, and so on. So so in this case, this f tilde n, you can write it as minus pi to pi dx f of x minus I and x. So this expression, like I have written down, uh, just following the idea, like how I'm writing this an and b. So this you can see an was the coefficient of cos terms. Like here you can see in this Fourier series expansion, in this a an's were the coefficients of cosine terms, and I, in order to get them, I I uh, like in order to calculate them, you have to see that like you have to apply this orthogonality condition, and upon doing that, you will find this expression for a. So similarly, if you want to get the value for bn, you can apply again the same authority condition. You will find this bn will come out to be this. Similarly, if I'm expanding my function in this Fourier series expansion, then this coefficients which are f tilde n, so you can expand them, I mean, you can write their expression just like how I wrote for ans and bns, by taking this integral. So you can see that the form actually matches quite exactly in both the cases. So this is n and this is back. The same like I have written here for f tilde. So so this f tilde like uh, then if you can see, if you our function is given f of x to be x. So if you go on to calculate, and then if you would integrate them uh, by parts, so send it twice. So you have to just basically do this integration, and then you'll find like this would uh, go like something this form. So if you would solve them, you would get this values. So these are be the values of f tilde n. So correspondingly for each given value of n, you will have a corresponding uh, coefficient value. So so f tilde 1 would be n equal to 1 in this case. So that will give you minus 2 pi I, and similarly f tilde 2, that will give you 2 pi I. Sorry, 2, that will give you pi I. F tilde 3 will give you 2 pi by 3 I. So on you'll get. But here in this case, like uh, you can see like for n equal to 0, uh, there is a issue. Like for n equal to 0, like you can see that this like uh, this is going to be undefined. So like here also, like you can write this expression after that when you consider n is not equal to 0. For n equal to 0, you can write this for n equal to 0, f tilde 0 is to 0. That is basically 1. Uh, that will be, you will see that if you do this integration, you will get 0. Because you can see this f tilde 0. Like I have written again in that way. Like you have to basically take the inverse to calculate the coefficient. Like earlier also the same thing which we did. This an and b. So here also, like if I'm uh, expanding this f of x in this way, then your like let's say the f of x I can write um, 1 over L, or you can just forget this 1 over L for now. So the first term, like for n equal to 0, that will give me uh, for n equal to 0, this will be, or let me just write this to you for clarity. This is n. Be f tilde 0, and, and let's say not equal to 0, this will be tilde. So f tilde 0 is the coefficient corresponding to e raised to the power 0. That is basically 1. So its uh, uh, inverse would go something like this, or this coefficient you can write in this way, just following the ideas of orthonormality which we started our discussion. So this entire thing goes by this the way how we retrieve this an and bn values. So that is the general technique if you want to calculate any Fourier coefficients, or any coefficients of a expansion of a function, or expansion of a function in terms of its orthogonal basis. So here, like we finally got the values of coefficients. So f tilde 0 is 0, and this f tilde 1, f tilde 2, f tilde 3 will be will be coming of these forms, which is decided by this f tilde. So you put values of uh, n for you put different values of n, you will correspondingly get the coefficient values. That is f tilde 1, f tilde 2, and so on. So, so, so are you able to follow this? You can just tell me like if you will not get anything. Hello. Okay, Nachiketa is fine with it. Uh, Akanksha, like, are you able to follow this? You do not have any question as of now, then we can move on. Like, but you can ask anytime you are having problem. So the next thing was on some special cases of Fourier series. So you will see that when we are talking about periodic functions, so these periodic functions, they often would be uh, having a particular sort of behavior. I'm talking about symmetric or anti-symmetric behavior, or otherwise like we call even or odd function type behaviors. So what are they? So again, this is something which would be taught well by Professor Aditya Sharma. So it would be there in your lectures already. So just to refresh again. So even functions like, or otherwise you see them as symmetry function. So why and how they are symmetric. So you see, like if a function is periodic, where x is defined under some range minus L to L. So that is, let's say we're talking about f of x equal to x squared. So you see that minus L to L, this function, uh, like you will see that this is even function. How, like above this point 0. you see the what is the behavior, like what is the behavior that is evolving on this right hand side, or the reason uh, uh, x greater than 0. You will see that like the same behavior is repeated on x less than 0. So or otherwise you can also check, you take for our f of x is given as x squared. So for x greater than 0, you say you take f of 2, so that will give you 4, and you take f of minus 2, that will also give you minus 4. So this is your x greater than 0, and this is your s less than 0 region. So in both region, the value is repeating, so the behavior is repeating in the same way. So that is the characteristic of a symmetric function, or otherwise we call even functions. So in this case, if you have this kind of functions, and you want to take Fourier series, then you can write the Fourier series something of this form. Here you will see that this bn terms that is missing out from here, because bn terms will not contribute, because you will see that again by using those orthogonality conditions which we were discussing earlier. So this bn will be 0, because this bn integral, like if you would follow, uh, or let me just tell you this after. So, so in this case, this bn will be 0. So I will tell you why it is.
Hi,
So,
I'm good. How are you?
but for
Ah,
hello,
right.
uh, uh, are you having anything doubt? Okay. So this a0 you can write uh, like again by the same orthogonality feature, by those same property. So that will give you this expression, and for n, that this will give you this expression. For bn, you will see that the expression would be something 0 to L f of x sine n by x by L. So you will see that the sine is odd function, uh, and this f of x is a even function. So there you will see that uh, as a whole, uh, this will this will be a odd function. So this is an odd function. So the odd function under this integral, they will give you 0. So that's why this uh, that's why this bn value will be 0 in this case. Same for odd functions. Like if you are having odd function instead, like let's say the function that you are considering to expand them in terms of Fourier basis. So um, yeah, so Fourier basis for a given odd function, you know this, they will have this condition. So uh, one of such example is this x cube function. You will see that for uh, every behavior of function for x greater than 0, that will be exactly the same behavior that will be repeated for x less than 0, but with a opposite sign. So that's why you will see that this function would be uh, like a the one which is on the right side would be the behavior would be same on the left side, but with the inverted one. So in this case, you will see that a0 and an values will be 0, because again by this uh, this feature which I was like discussing here, this orthogonality conditions or the properties which you will apply them, you'll find that uh, this a0 and an values will be giving you 0. because again they will become a odd function and their integral is. And same for this, and when you do for this Bn integral, you'll find that this Bn integral is a uh, will give you non-zero value, and that is defined in this way, because this Bn integral will be basically a integral over even function. So integral over, yeah, even function. So that is a non-zero value. So if you would integrate out under the limits. So let's select one such example we can take is maybe the first example, like the one which we started in the previous problem. So if we take f of x equals to x, which is defined minus pi to pi. So, and you have to let's say we are considering this function and calculate the coefficients or Fourier series coefficients. So you see this f of x equal to x. This is a odd function. So like as we found for odd function, this a0 and are 0. So basically you can just simply uh, write there that by the property of odd function, Fourier series expansion will not contain this uh, term corresponding to a0 and a. So basically what I mean here, first of all, you can just identify what this uh, range and I mean the integral which you will take under the range, you have to identify from this given condition. So let's say, like as I was telling, uh, you have to calculate this integrals a0, which I initially wrote. So initially I wrote for a specific case, but in general, a0 is given in this way. So where this b and a are the values denoting your interval, like the starting value of the interval is a, that is given minus pi, and b, that is pi. So and your f of x is given as x. If you would calculate that, that will give you 2 over 2 pi minus pi pi x dx. So that is 0. So same you can also check for an. So in general, this an is given. Let me just emphasize this. This is true for any generic form. So this is for an. So here an, if you would calculate, again you know this value of a and b and your function, you will see that 2 over 2 pi minus pi 2 pi, and your f of x is x, and this is 2 pi and x over 2 pi, because b minus a is 2 pi. So here you will see that your x is odd function, and your this cos n x function, basically 2 pi and 2 pi will go away, and cos nx is an even function. Together, this is a odd function, and its integral will give you 0. So n is also 0. So that is intuitive, like, or basically, like, if you just can judge what is your function, if the behavior is symmetric or anti-symmetric. Based on that, you can guess like which coefficients will give you non-zero value. So in this case, our function was odd function or anti-symmetric. So a0 and an will be zero for sure, and basically you have to calculate bn. So, uh, but for any other general case, if you do not know the behavior of the symmetric or the symmetric behavior of function, or even whether that is even or odd function, then you should check by this formula. Otherwise, like, you can easily guess that which will be zero or not. But here our function is odd, so we know bn will be obviously will give you non-zero. So bn, the general formula is, this is your general form of your bn. But since like we are having this is odd function, I already give you a specific form of bn. If your function is already a uh, odd or even function, like in this case we are having odd function, this bn will be of this form. So you can easily write this, or you can also see from this formula we can get there. So maybe like I'm using the one which I showed you about. Let me say this equation is uh, a. So from equation a, so you can also get this uh, from here also, and so that will give you 2 over pi. And let me see, I think, okay. So I have to see, yeah. So this is defined for minus L2, this x. So yeah, so you can use this formula, 2 over pi and a to b, or that is 0 to, so 0 to L, so L will be pi. So in that case, minus L to L was your interval. So here in this question, the interval is defined minus pi to pi. So that means minus L is your basically minus pi, and L is your pi. So that is the interval you are working on, and your f of x is x. Then sine n x over pi. So I have just used that equation A form, and you will see that, like, if you do this integration, this is basically 2 over pi 0 to pi x sine nx. So this will give you non-zero value. So just you have to integrate this again, and you will find this will be non-zero. So that is the uh, thing that you see when, if your function is having even or uh, odd, like behavior, or what I mean, if they exhibit symmetric or anti-symmetric behavior, you can just easily see like which coefficients will be zero or non-zero. If it is even, then uh, bn will be 0, and a0 and an will be non-zero, and you can calculate them from these expressions. And if it is odd, a0 and an will be 0, and but bn will give you non-zero, so you can calculate from bn from here. Otherwise, if you don't know the behavior of your function, whether that is even or odd or symmetric or anti-symmetric, then like this is anti-symmetry. So in that case, you can use these expressions a0 and bn. So if you don't know whether your function is symmetric and symmetric, you have to calculate all of them. Like any given arbitrary coefficient would be non-zero or could be zero. If you do not have any idea about you do not have any idea about the symmetry of the function. So that is for even and odd like functions and their corresponding Fourier series expansions. So then you can just simply expand uh, like in this way after you know this a0 an values. If your function is even, you can write your function in this expansion. And uh, if you're doing it for odd function, so you can write, your Fourier series expansion. Sine. So this will be a Fourier series expansion for odd function. You have to first calculate this coefficients bn, and then you can just expand in this way. So 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 here in this question, like your function is given uh, half multiplied with pi minus x uh, with period 2 pi, and it is defined in 0 to 2 pi interval. So uh, so let's say if you like if you can want to check the um, whether this function is even or odd, for like first of all, like since this function is defined for 0 to 2 pi, that means like you cannot say that this function is symmetric or anti-symmetric about 0, because we always say symmetric or anti-symmetric about a point. Like here also, like what I was telling you, since our function was defined from minus L to L, so we were telling that this function would be anti-symmetric or symmetric about 0. So in any other case, like if that is given, you can basically check from your a0, an, and bn formulas whether your coefficients will be 0 or non-zero. So let's say if this function is given and we have to write its Fourier series expansion. The basic thing you have to do here, starting by calculating the Fourier coefficients. So we'll calculate first a0. So you will just apply the same rules again. So for a0, like as I said, you have to work out this formula. So first figure out what are a and b. So in this case, b will be sorry, yeah. So in this case, b will be 2 pi, a will be 0, since our interval is goes from 0 to 2 pi. So this is your a and this is your b value. So you apply that formula 0 to 2 pi. So sorry, f of x dx. So our function is, so when you will calculate this, you can check that if you would calculate 1 over pi 1 over 2 pi minus squared by 2 0 to 2 pi. So this will actually give you 0. Like if you would calculate, if you just put the uh, limits of this integral, so you will find this to be 0. The same you will calculate for ans. So an again you will follow the same formula, that is 2 over b minus a, and b minus a is 2 pi, and your integral is from a to b, that is 0 to 2 pi. And f of x is half times pi minus x, then cos of 2 pi n x by b minus a. So this is the formula I'm using. So let me say that this is b and this is c. So I wrote this from equation, this is from c. So yeah, there is a slight mistake here. This will be sine, not cosine. So here it is multiplied with cos 2 pi nx by b minus a. So 2 pi nx, b minus a is 2 pi. So if you do this integral, uh, here also you will find that is actually to calculate this integral, you'll find this will also give you 0. So I'm skipping those steps. This is just basic integration you have to do. And now you have to calculate bn. So if bn's are also 0, then you cannot expand this function in terms of Fourier series. So we hope this is not 0. So and this comes from, let's say, this this expression which I showed you earlier. This is, let's say, this is t. You apply the same uh, yeah, and you apply the same substitution here also. Then here you will find this is 1 over 2 pi 0 to 2 pi I minus x sin nx dx. So if you would do this integration, I minus x cos nx sin nx square 0 to 2 pi. So just I'm doing this integration by parts. So if you again put these limits and you will simplify, and that this will give you 2 pi over n plus pi. So this bn is actually 1 over n. So if it is b1, that is 1, b2 is 1 over 2, b3 is 1/3, So and so on this goes. So only Bn is the non-zero Fourier coefficient value, uh, or else other coefficients are zero. So a0 is zero, so do an are also zero. So only Bn gives you non-zero value. So now you can write this function in terms of Fourier series. So here, okay. So when you have f of x, so if you have to write it in terms of Fourier series expansion, uh, what you have, like how do you write? So as earlier we started by defining them. So the first term corresponds to a0, and other terms cos 2 pi and x by b minus a. So this is your formula, or the form uh, for any function. You can write there any periodic function. You can write their Fourier series expansion in this form. So like this boxed forms which I have given here, they are like some generic formula which you can apply for in various places. So like they are generic in the sense like if you're given any periodic function, you can always apply these formulas. You can always use these formulas. This one. So this is f of x, Fourier series expansion of this function f of x. So now we have our function half times pi minus x, and a0 we found out to be 0. Ans are also 0, but bns are non-zero, and this b minus a, this actually, this factor is basically sine. This factor is basically sine nx, because b minus a is 2 pi. So you can write for, yeah, for b1 you have this b1 equal to 1. So the first term of this series expansion will be sine x. The second term will be half sine 2x, and so on this will go. So uh, so basically you are, maybe I need a basically, so I'm writing my function which was given uh, in terms of Fourier expansion, where only bn's were 0, that is this term. So I can write it down as n equals to 1 to infinity. Bn was 1 over n and sine nx. So this is a Fourier series expansion, and but with that there was also one additional question. Uh, After doing this Fourier series expansion, you have to prove that, like, or you have to uh, or yeah, you have to calculate the value of this series. So you can use this expression or use this Fourier series expression, Fourier series expansion to calculate its value. You see, like if I take x equals to 0, this case RHS, in RHS of this equation, for x equals to 0, that is sine 0, that means uh, uh, not x equals to 0, like here I have sine and x, like if I use sine n pi by 2, like why I'm doing so, because I need a sum which is given in this way. So 1 minus 1 by 3 plus 1 by 5. So if I take x equals to pi by 2, here in RHS you see I can write it as x equals to pi by 2. Or let's say the first term, for n equals to 1, sine pi by 2, then sine 2 pi by 2, then I will have 3 sine 3 pi by 2. So on you will have. So I'm just using for x equals to pi by 2. So here you will see on RHS, this gives the other terms as well. So next term would be sine 2 plus sine pi and so on. So here after this 1 over 3, that is sine 3 by 2 is minus 1. So this term will become minus 1 over 3. And the next term is sine 4 pi by 2, that is sine 2 pi, that is 0. So 0. Then the next term is sine 5 pi by 2, that is 1. So that will be 1 by 5. So you see, like I'm getting some series of this form, which is what exactly asked here. So 1 minus 1 over 3 plus 1 over 5. The next non-zero term would be minus 1 over 7. So you can check that that will be the term corresponding to sine 7 pi by 2. So here you will keep like doing this, you will find you will get more terms, non-zero terms. So then finally you can write, if that is so, then 1 minus 1 3 plus 1 over 5, then 1 over 7, this will be equal to this term. So that is pi by 2 pi by 4. So that is the uh, last part of the question, which was asked to calculate the value of this series. So that will be pi by 4. Yeah, that was about that. So okay, Nasikta, if you are only around here, so you are able to follow this, no? Hello. Okay, thanks. So the next part is the complex form of Fourier series. So like uh, since like yeah, we were discussing about periodic function, and we are expanding them, like non-sinusoidal periodic function into sinusoidal periodic functions using Fourier series expansion. So like we were expanding in terms of sines and cosines. The same thing you can also expand in terms of this exponentials. Why? Because this exponential, after all, they are itself is a linear combination of some sines and cosine. because like you can write this, if this, let's say this e to the power I theta as uh, sine theta plus cos theta 2. So like these exponentials are also they themselves are linear combinations of this sines and cosines. So yeah, so I think this is also, like, if you can check your lectures which should be uh, taught to you already in this week, the like you can expand the same Fourier series of a given function, uh, which you are expanding in terms of sines and cosine, again in combination of exponentials, or again in a different combination, which will be a exponential series. No, exponential series in the sense like you are expanding that function in terms of exponentials. Like here you will see that the first term would be corresponding to n equal to 0 or n equal to 1, n equal to minus 1, n equal to 2. So like for n equal to 0, this will be simply c1. For n equals to 1, this will be c1 e raised to the power 2 by x over b minus a, and c2, then this will go 4 by x over b minus a, and so on. So this way you expand this or you do this Fourier series expansion without this exponentials. So that is basically the complex form. So in this case, like again, I have written down some general like formulas which you can always apply them if you are taking a Fourier series expansion of a non-periodic, non-sinusoidal periodic function. Then you can always use these expressions. And again, if you are having even function, so this is for a special case. If your function has symmetric behavior, you can use this uh, uh, property. And if it is uh, antisymmetric, then you will see that your Cn will only be equal to minus I by 2 Pn, because n will be 0. Same thing which we found out earlier, like because n and a0, they are 0 for odd functions. So you can see a example, like suppose, so your f of x is given to be minus e raised to the minus x, and again here, like you don't know its behavior, like uh, I mean here check, like the interval is defined from -1 to 1. So about x equals to 0, you can see that the behavior is not same. It is not neither symmetric or nor anti-symmetric. So you don't know, like like which ans or bns should be 0 or non-zero. So what you can do, like you and since the question is asked about write the complex form of Fourier series expansion, you can just use this relation. And since you don't know about the uh, behavior of this function, whether it is even or is better, you can start with this. You start with this uh, expression of Cn, and you will get the coefficients, Fourier coefficients, and then finally you can write a Fourier series expansion according to this formula. So first you have to calculate Fourier series coefficients, that is Cn. So here it is given 1 over b minus n. So here b is 1, a is -1. So that is 1 over 2. Then limit goes from -1 to 1. Minus x is your function. And this is exponential of side 2 pi and x 2 pi. So that is half minus 1 I and pi dx. So if you do this integration, you find this uh, coming out to be something of this form. Sine parabolic. So why I'm writing the sine hyperbolic, like here you will see that after doing this integration, and when you will put the values of this integral limits, you will get something of, or basically I'm using this property. If you have something of this form, you can always write it to be sine hyperbolic theta. So that is what here also I have done. You will see that after integral and then when you put the values, so this will be something uh, e raised to power e raised to power minus 1 over 2. So that I have written sine hyperbolic 1. So that is this part. So yeah, so this is your Fourier coefficient, and yeah, it's like if you let me check whether this is correct or not. Like I'm not sure. This is half. So if you do the integration, you'll get x integration of this exponential is this exponential over minus 1 plus I n pi, and the limits are minus 1 to 1. So so sin minus 1 sin n pi. So here, like what you can write this thing. So this e raised to power minus I pi. You can write this to be um, minus 1 to the power, because you can see like if you put uh, odd values of n, you will get a negative or minus 1. If you put even values of n, you will get plus 1. So in short, you can write this minus 1 to the power n will be the value for uh, or basically this is the same thing. Or let me write this here. So minus I n pi equal to I n pi minus 1 to the power. So this is minus 1 to the power, and this is also minus 1 to the power n. and you can take that to be common. Say common factor, when you pull that out, then yeah, then you will get that form which I was earlier telling. So this is minus 1 to the power n 1 plus I n pi sine hyperbolic 1. So sine hyperbolic 1, this comes from this relation. So I hope you are familiar with this sine hyperbolic relation. So that is just the value of C. So this is just like the simple technique that you are just going through. Just you know the Fourier series expansion form. So these are the forms of Fourier series expansion f of x, and for that you need Cn. You have to calculate Cn. So this Cn, the Fourier coefficient forms are defined in this way. So when you have this form, just you follow the like range and limits, and just you have to calculate this integrals. So that is what we were doing all throughout this session, even in earlier problems which we were doing for sine and cosine. So you just try to figure out the form, and then you frame a formula for that, or the form which like I think this would be the same form which would be given to you in your uh, lectures that is uploaded on your NPTEL portal. If not, like they basically won't differ much. So this the notation that I am using here could be different from the notation which would be there. But otherwise, after all, this expression will hold true whenever you are asked to do a Fourier series expansion for a given non-sinusoidal periodic function. So that is the uh, complex form of Fourier series expansion. So yeah, so if it is clear for you, then we can move. Or if you have any doubts, you can say. Do you have any doubts? If not, then we can. Okay, fine. So we can move on for the next thing. So that is Parseval's theorem. So this Parseval theorems, like here I've given their mathematical expressions. So basically, like I think again, this is something you will find, or you would have already found out from your lectures that was uploaded for this week. So which I think Professor have already explained to you this very well. So basically, this Parseval's theorem come into use when you try to calculate this square average integrals, which you basically relate them with uh, Fourier coefficients. So these are Fourier coefficients. So a n prime are the Fourier coefficients of functions f and g respectively. Same this bn prime and a0 and a0 primes are. So that is what Parseval's theorems gives you, and it also helps you in calculating this uh, RMS values, because RMS values involve something square root of uh, some integral squared average f squared. So this RMS values, like you can easily calculate them if you can able to like do a Fourier series expansion of those of the function that is asked to you. So like if you want to do this square integral average, you can like if that means if your f and g functions are same, that is you're taking the square integral average, that that will be equal to this. So uh, here I have just given the form. So again, for any details, like you can check back into the lectures, or also you can ask here if you have any doubt. And this is for the complex form. So if you're uh, like if your Fourier series expansion is given in terms of a complex form, like the one which we did just before here. So this is a complex form of Fourier series expansion, and in that case, you can relate your uh, Fourier series coefficient Cn with the square integral average by Parseval theorem. That is, that will be of this form. So I think this can be clear, like if we just quickly go through a problem. So let me, yeah, yeah, we can see this problem. So yeah, f of x is given to be x squared, and here x is defined from limits from in this limits minus pi to pi, and this is the periodicity that your uh, your period for this function is 2 pi. So after every 2 pi intervals, this function repeats, and the Fourier series function is already given to you. That means you see these coefficient values, particularly this one. These are Fourier coefficients. These are basically uh, ANs, and this corresponds to A0 or A0 by 2. Uh, Here you don't have BNs. BNs are 0 since you have a symmetric function, a even function. So so that's why in this Fourier series expansion of this function, you will never get Bn. You will always able to expand them in the orthonormal basis of cosines. So cos x, cos 2x, cos 3x. And so if that is so, then the follow-up question to it is that like you have to calculate if this is your conditions given to you. If the Fourier series expansion of the function is pi square by 3 plus plus, the part which is given here. So if that is given to you, then you have to calculate this expression, the sum of this series. So let's see that in order to calculate this sum, like for a moment, if you would see this coefficient and like if you just uh, look for all values of n. So if you start with n equal to 1, so you see in the denominator it is n square. So if you take n equal to 1, it would be 1 square. For n equal to 2, it would be 2 square. And for n equal to 3, it would be 3 square. So the thing is like using this Fourier series expansion, like it gives you intuition that you have to take a square of this function so that like this n square which is coming out here, that would be uh, that would go like n to the power 4, because here you have to calculate a series which is like uh, the the series which in which the series goes like 1 over n to the power 4. So 1 by 1 fourth plus 1 by 2 to the power 4 plus 1 by 3 to the power 4 and plus so on. So you can use in those cases you can use Parseval's theorem. So let's say this is the uh, form you have to use in order to calculate that series. So f of x is given to be x square. So you take that square integral average of that function. That is, x square. Uh, you square the value of x square. That is x to the power 4, or you take the square of that x square function, x to the power 4. Integrate it under the limits a to b. So in our case, the limits are minus pi to pi, and then you equate it with the Fourier coefficients. So that is what the thing which you have to do. So Let me proceed. Like you can see how follows through. So here, let me write like the things which is provided to you. A is given to be minus pi. Those are limits. A and B is given. So do A0 by 2, the first term of your Fourier series expansion, that is pi square by 3. So that means A0 square by 3. And also An is given. So N is 4 square. This 1 to the power n. B is 0. So now from Parseval's theorem, to take this square integral average and just use this form. So I'm using this second expression over here. So that is b minus a by 2, then multiplied by a square by 2 plus and the rest part. So b minus a over 2, that is 2 pi by 2. Half of square by 3. Summation goes from 1 to infinity. 16 is 1 about 2 plus b inside 0, so that will be 0. So just I have used this form. Summation n equal to 1 to infinity n square plus b n square. So n was this, so its square will be 16 over n to the power 4 multiplied to minus 1 to the power 2. So now you see you're getting this n to the power 4. So now you can like feel that you can able to uh, get a value for this series if you would expand them for different values of n. So just you can proceed on for the uh, uh, rest part. Like you just have to take the integral on LHS and you will get your answer there. So this is you take the integration. See this. So keeping only uh, this part, this vector which is under this parenthesis, and then taking rest of the things to the other side of the equation, you see I can get expression. This is equal to, so uh, you take to the other side, then you have to just uh, add two terms corresponding to this, and then you to divide them by this uh, vector of 16. I think uh, it's pi and pi, or 1 pi and like 1 pi would cancel from LHS and RHS, and then just this is just basic algebra. You do this and you will get this pi 4 to the power 9. So this is how you use Parseval's theorem. Like it easily helps you to give this square integral average values. So are you able to follow this? Hello. Okay, thanks. So there is one more to it. So like that was like the Fourier series expansion. Here you can see the question asked for this case where the Fourier series expansion was taken in terms of cosines. And but when you have Fourier series expansion, the form is given in terms of exponential. That is, you have to use the forms of complex Fourier series expansions. So uh, maybe if you would work this out, you will get again. So let me do this again. So the form that you have to use now, which I am already written above. So just for the ease, like I am writing down here too. So this is the form which you have to use. So this is the quantity which you have to calculate. So I'm using this form which I showed you, the different forms of Parseval's theorem. So again, just you have to figure out what is your A, that is your lower limit where this periodic function is defined, and P is pi, and your function is so negative x. So then you do this. And then you equate it with this b minus a. So that is e raised to power minus 2x, and its integration then again you e raised to power minus 2x over minus 2, and yeah, b minus a is 2 pi sum vector sum from. So yeah, from here you can calculate the summation of this Fourier coefficients. That will be 2 plus 2. So that is so here again you can see I can write this sine hyperbolic of 2 pi, because earlier as I told you sine hyperbolic of theta, you can write e raised to power theta minus e raised to power minus theta over 2. So just you apply this form here, then finally you can write this form of summation of this cn square, which will give out to you this way. So this is the same thing which I uh, did also. I had this expression. So right here. So this is something like I was explaining how you can write this uh, complex form of Fourier expression, but the thing is like it is not this relation that is how you write, but what I mean there was like you can, since you can write exponential functions in terms of cosines and sine, that is like if you have some cos theta, you can write e theta over 2. So similarly, you can write also sine theta over e theta minus theta over 2. So since you can write sine and cosine in terms of this exponential uh, uh, of I thetas, so that is the reason you can write this uh, Fourier series expansion in terms of this exponential, because after all that is a linear combination of sines and cosines. So that is just like you are still in the same basis of sines and cosines, but you are just writing it down in a different way. Uh, After all, like whichever form you use, or complex Fourier series, or your like this sine and cosine Fourier series expansion, both are, after all, they are sine and cosine series, because you can write this exponential in terms of this sine and cosines again. So if you say like I can write ei theta to be some like if you add them cos theta and sine theta, and see, or basically you can write this ei uh, to be some, or I mean like if you would simply write cosine theta, sorry, cos theta plus I sine theta. So this is your familiar uh, like Euler's relation. Sine theta. So so that these relations, or basically if you would use both this relation, you can individually get what cosines and sines. So uh, they are like all related to each other. I mean that is they all actually come from this Euler's relation, this ei theta, which is equal to cos theta plus I sin theta. So if you would apply these ideas, then the Fourier series expansion, the definition with which we started our session, the entire thing, you can using this relation in those definition. Initially, what we wrote down for Fourier series expansion, which we were expanding for given function f of x in terms of some a0 plus an sin nx, sorry, an cos nx plus bn sin nx. So you can again write them uh, in terms of exponential when you use these relations. So that is the same thing. There's nothing different happens for complex Fourier form of Fourier series. So earlier I wrote a like uh, a different form of like expressing ei theta of cos theta plus some sine theta over 2. So that was not the exact form which I was referring, but this is the exact form I mean. So apologies to that, like I meant something different, which I just simply want to say that you can write them as linear combination of cosines and sines if you for any exponential uh, of I theta. So yeah, that was I was trying to say. And so yeah, this is your exponential mm, complex form of Fourier series. So if you um, have any doubts or question, like you can ask or you can. So Nachiketa, so are you able to follow this or like, or do you have any problem in understanding or do? So do you have any questions, any doubts? No questions. So like if you are able to follow all of this, then you're doing good. So you're following the lectures well. So then you could also able to solve assignments. So I hope you are solving them as well. So I think it is already half the way for your course. Like you are over the half the way in this NPTEL course. So so there is rest half. So in this rest half, there will be a lot of things that would go, and if your basics are good by then, so then you can able to like finish this course very well. So just keep practicing as many problems as you can like get your all problems sorted for like from all the resources that is provided to you by NPTEL, like your lecture videos, like they are really well explained. You can find uh, like every detailed explanation there, and also notes are regularly updated to you. Also, this problem solving sessions that we are doing here, even like what I'm trying to present here on my iPad, like the courses that I discuss here. So that is also shared to you, like because I share this uh, discussion to you. If in any case, if you find like something useful, like you can refer to it, or otherwise, uh, other materials are well provided to you. So if you would wisely use them, like you can get through, you can understand this course very well. And this is a very important course. So just never miss out any single topic or any single concept of this course. So each and every bit of it will come into use in some way, in some form. In your future, like if you study physics or even in other fields, there are many fields. This course is very useful. So just go through them. So there's nothing more I have I've got I mean more I would go into right now, maybe because it is already the time is nearing so the time is up, so can discuss more on the next week problem solving session. And yeah, if you still uh, if you're having any problem in some way, like in understanding any concept or also assignment problems, you can yeah. So can you recommend a book for more problems? So I think some books will be already recommend to you, but I would say like for uh, these things which we are discussing, so maybe like this Fourier series, like when uh, refer Mary L. Boss. So like Mary L. Books, like if just let me write down here so you get the name properly. This is Mary L. Boss. So if you follow this book, like this is like well written, and we'll find it on these questions which we are discussing here. Get it from there. You can get different forms of questions, and also correspondingly there will be details of those concepts. It is properly explained. I think you can understand them if you start following from the beginning of this Fourier series. So there will be also ample of problems. So that would be good fit for solving out problems, because those problems will be there with the mindset of right application. Because you will see that in that book, uh, the questions will be of something of a application. I mean, like this force is like we are just discussing in the context of some mathematical structure, but there you will also find as in terms of its application to various problems in physics and so on. So this would be a good fit for you. Like if you would follow this, this will be great. Also, apart from the like uh, uh, so um, mm, more questions in the sense do you mean like you want to practice more questions apart from assignments, or is there something like some new sort of questions, or some specific kind of question that you want to practice just to begin from the I mean from the start? I mean, but I mean in general, if you follow a book, so there will be questions like they would start from easy one to more complex ones. So so you would follow a book, then that would be a very nicer one. But I would suggest never miss out to follow this assignment questions, and also the discussion that we are doing here, particularly your assignment question and also the questions which is discussed in your lectures. Those are really handful of them, which you can find it very useful even when you move forward in your future. These courses will come in one or the other form every now and then, so just never miss them. But for more questions, as of now, you can follow this book, or also the books which is told to you. You can also check them. So is that fine, or do you have any more questions or any? Okay, so if that is so, then there is no more questions, then maybe we can check later. We can see each other. I can see next week for. Uh, I think we would be discussing this Fourier series again. We'll discuss some problems related to Fourier transform. So then we'll proceed through from there. So okay, then see you bye.